Hello and welcome to the Sleepy Equation, where the universe hums softly and science tucks itself gently into the folds of the night. If you're easing into rest, wrapping yourself in the calm of evening, or simply searching for something steady to carry you into sleep, you're in just the right place. Tonight, we're floating far beyond Earth to a realm where stars collapse and matter is squeezed into something so dense it defies imagination. It's the story of neutron stars, how they form, why they weigh so much, and what their silent gravity tells us about the very structure of space and time. Before we begin, I'd love to know how long it takes for you to fall asleep to these videos and where you are watching from. Whether it's dusk in the city or just before dawn in the countryside, I'm glad you found your way here. Take a long, quiet breath, let the noise of the day fall away. Let's begin. Imagine, if you will, the quiet aftermath of a star's final breath, a moment suspended in the vastness of space, where the laws of physics bend to their limits and something extraordinary is born. This is the story of neutron stars, the universe's most dense and enigmatic objects, forged in the fiery crucible of a supernova. Their existence is a testament to the delicate balance between gravity and quantum forces, a dance of destruction and creation that leaves behind a relic so compact, so unimaginably dense, that a single teaspoon of its material would weigh as much as a mountain. To understand how such an object comes to be, we must first journey back to the life of a massive star, far larger than our own sun. These celestial giants spend their lives burning through their nuclear fuel, layer by layer, like a candle slowly melting away. For millions of years, they shine brightly, their cores fusing lighter elements into heavier ones, hydrogen into helium, helium into carbon, and so on, until iron begins to accumulate. Iron is the ash of nuclear fusion, a dead end in the star's energy production. And it is here, in the silent accumulation of this unyielding element, that the star's fate is sealed. When the core can no longer support itself against the crushing weight of its own gravity, it collapses in a fraction of a second. The outer layers of the star, no longer held up by the energy of fusion, come crashing down in a cataclysmic explosion, a supernova. For a brief moment, this dying star outshines entire galaxies, scattering its enriched remains across the cosmos. But in the heart of this chaos, something remarkable remains: the core, now compressed into a sphere no larger than a city, yet containing the mass of 1.5 suns. This is the birth of a neutron star. The density of such an object defies earthly intuition. If you could somehow scoop a fragment of this star and bring it to Earth, it would slice through the planet like a knife through warm butter, pulled inexorably toward the center by its own unimaginable weight. The reason for this density lies in the star's composition, a sea of neutrons packed so tightly together that the empty space we take for granted in everyday matter is entirely erased. In a neutron star, atomic nuclei are pressed shoulder to shoulder, their protons and electrons forced together until they merge into neutrons, leaving behind a substance that is, in essence, a single gigantic atomic nucleus. Yet, despite their incredible density, neutron stars are not lifeless husks. They spin, some hundreds of times per second, their surfaces crackling with magnetic fields trillions of times stronger than Earth's. They glow with residual heat, remnants of the supernova's fury, and some even pulse like cosmic lighthouses, sending beams of radiation sweeping across the universe. These are the pulsars, the timekeepers of the cosmos. Their rotations so precise, they rival the most accurate atomic clocks on Earth. But the story of neutron stars does not end with their formation. They are dynamic, evolving objects, shaped by the extreme conditions within them. In their cores, where pressures exceed even those found in atomic nuclei, matter may take on forms so strange that they exist nowhere else in the universe. Some theories suggest that quarks, the fundamental particles that make up protons and neutrons, might break free from their confines, creating a swirling soup of exotic matter. Others propose that neutron stars might harbor cores of hyperons or even Bose-Einstein condensates, states of matter so alien that they challenge our very understanding of physics. As we drift deeper into the mysteries of these stellar remnants, we begin to see them not just as curiosities, but as cosmic laboratories, offering glimpses into the behavior of matter under conditions impossible to replicate on Earth. They are the universe's way of pushing the boundaries of what is possible, of showing us the hidden layers of reality that lie beyond our everyday experience. And so, as we prepare to explore further, let us rest in the quiet wonder of these celestial marvels, their silent spins echoing across the light years, a reminder of the beauty and strangeness of the cosmos. Let's continue this journey into the heart of a neutron star. I'll gently guide you deeper into the science and poetry of these incredible objects in the next message. For now, let the image of a spinning neutron star linger in your mind, a tiny, dense beacon in the vast ocean of space. As we drift deeper into the mysteries of neutron stars, let us imagine ourselves floating toward one, not too close, for its gravity would pull us apart atom by atom, but near enough to sense the quiet hum of its existence. From afar, it appears as a smooth, almost perfect sphere, its surface a crystalline crust of iron nuclei locked in a lattice so dense that mountains, if they could form, would rise no higher than a few millimeters. Yet beneath this thin, fragile shell lies an ocean of neutrons, a quantum sea where the rules of our everyday world no longer apply. To understand what lies within, we must first shrink ourselves down to the scale of an atom, or rather, what was once an atom. In ordinary matter, atoms are mostly empty space, with electrons whirling at vast distances from their nuclei. But in a neutron star, gravity has erased that emptiness. The immense pressure has crushed electrons into protons, merging them to form neutrons, until the entire star becomes a single continuous fluid of nuclear matter. Picture a crowd of people pressed so tightly together that they merge into one entity, their individual identities lost in the collective mass. This is the state of matter inside a neutron star, a place where the very concept of empty space ceases to exist. The core of a neutron star is where physics becomes poetry. Here, densities reach over 1 billion tons per cubic centimeter, and the neutrons themselves begin to behave in strange and wondrous ways. Under such extreme conditions, they are no longer mere particles, but instead exist as a superfluid, a frictionless quantum liquid that flows without resistance. If you could stir this neutron soup, it would continue swirling forever, never slowing, never losing energy. This phenomenon, observed in laboratories on Earth at temperatures near absolute zero, occurs naturally in the heart of a neutron star, where the sheer density forces matter into this exotic state. But the true magic lies even deeper, where pressures grow so intense that neutrons themselves may break apart into their constituent quarks. Quarks are the building blocks of all matter, usually forever bound inside protons and neutrons by the strong nuclear force. But in the core of a neutron star, some theories suggest they might finally be liberated, forming a quark-gluon plasma, a state of matter that hasn't existed freely since the first microseconds after the Big Bang. If this quark matter exists, it would be the most perfect liquid in the universe, a remnant of creation itself, hidden beneath layers of unimaginable density. Yet neutron stars guard their secrets well. Their interiors are so extreme that even our best theories can only guess at what might lie within. Some models suggest the existence of pasta phases, layers of nuclear matter twisted into shapes resembling spaghetti or lasagna sheets. Their structures dictated by the competing forces of gravity and nuclear interactions. Others propose that the very center might contain strange matter, a hypothetical form of quark matter so stable that it could convert anything it touches into more of itself. If true, this would mean that some neutron stars could be strange stars in disguise, their true nature hidden beneath a thin crust of ordinary neutrons. All this complexity gives neutron stars a kind of cosmic personality. They are not uniform spheres, but layered like an onion, with each stratum governed by different physics. The outermost crust is a brittle, crystalline solid, while just beneath it, neutrons drip like rain from atomic nuclei, forming a kind of quantum dew. Deeper still, the neutrons merge into a superfluid, and at the very center, if quark matter exists, the star's heart might be a droplet of primordial soup, a relic of the universe's fiery birth. And then there are the magnetic fields. Some neutron stars, known as magnetars, possess fields so powerful they could erase the data from every credit card on Earth from halfway across the galaxy. These fields are born in the star's turbulent infancy, amplified by the rapid rotation and convective currents of its newborn core. When a magnetar's crust cracks under the strain of these fields, it releases starquakes, cosmic tremors that send ripples through space-time and unleash bursts of gamma rays, the brightest explosions in the universe since the Big Bang. As we contemplate these wonders, let us remember that neutron stars are not just curiosities, they are time capsules, preserving states of matter that otherwise vanished from the universe eons ago. They are also alchemists, forging heavy elements like gold and platinum in their violent mergers, scattering them across the cosmos to one day become part of planets, oceans, and even the rings on our fingers. For now, let this image linger in your mind. A tiny, spinning star, no larger than a city, yet holding within it the secrets of quantum matter, the echoes of the Big Bang, and the promise of cosmic gold. In the next message, we'll explore how these dense remnants interact with the universe around them, how they spin, pulse, and sometimes find one another in the vast darkness of space. But for now, let the gentle thought of a neutron star's superfluid core carry you deeper into relaxation, a reminder that even in the coldest reaches of space, there is movement, there is flow, and there is beauty beyond imagination. As we continue our journey into the heart of these extraordinary stellar remnants, let us turn our attention outward to the way neutron stars move through the cosmos, how they spin, pulse, and sometimes find one another in the vast darkness of space. There is a rhythm to their existence, a slow and steady cadence that has carried on for millions of years, undisturbed but for the occasional cosmic event that sends ripples through the fabric of space-time itself. Picture a neutron star as it first emerges from the ashes of its progenitor star. It is born spinning, a consequence of the conservation of angular momentum, the same principle that causes an ice skater to spin faster as they pull their arms in. The original star may have rotated slowly, but as its core collapses into a sphere just 20 kilometers across, that rotation accelerates dramatically. Some neutron stars complete hundreds of revolutions every second, their surface is moving at a significant fraction of the speed of light. This rapid spin, combined with their intense magnetic fields, transforms them into cosmic lighthouses, sweeping beams of radiation across the galaxy with metronomic precision. These are the pulsars, the most well-known variety of neutron stars. Their name comes from the pulses of electromagnetic radiation we detect as their beams cross our line of sight. Imagine standing on a distant planet, watching a lighthouse on a faraway shore. Each time the beam sweeps past you, you see a flash of light, a pulse. Pulsars operate on the same principle, but instead of light, they emit radio waves, X-rays, or even gamma rays. The regularity of these pulses is astonishing. Some pulsars rival atomic clocks in their precision, their rotation so stable that they can be used as cosmic timekeepers. The first pulsar discovered had a period of 1.337 seconds, a steady heartbeat that initially puzzled astronomers so much they humorously labeled it LGM-1, short for Little Green Men. But not all neutron stars are so orderly. Some, like the magnetitars we touched on earlier, are racked by immense magnetic activity. Their fields are so strong that they can twist the very crust of the star, causing starquakes, cosmic versions of earthquakes that release tremendous amounts of energy. These quakes can produce sudden, unpredictable bursts of X-rays and gamma rays, lighting up the sky for brief, brilliant moments before fading back into the quiet hum of their normal rotation. Then there are the binary systems, where two neutron stars orbit one another in a slow, spiraling dance. These pairs are among the most fascinating objects in the universe, not just for their rarity, but for the spectacular events they can produce. As they orbit, they lose energy in the form of gravitational waves, ripples in space-time predicted by Einstein and first detected in 2015. Over hundreds of millions of years, this energy loss causes the stars to draw closer together, their orbits tightening until finally they collide. The merger of two neutron stars is one of the most violent and beautiful events in the cosmos. For a brief moment, the collision outshines an entire galaxy, producing a kilonova, an explosion that forges heavy elements like gold, platinum, and uranium in its fiery crucible. The gravitational waves from such an event, detected for the first time in 2017, carry with them the story of the star's final moments, a story written in the language of space-time itself. And what remains after such a collision? Sometimes, a larger neutron star is born, its mass pushed to the very limits of stability. Other times, if the combined mass is too great, the merger results in a black hole, the neutron stars disappearing forever behind an event horizon. But before they vanish, they leave behind one last gift: a spray of newly formed elements, ejected into the interstellar medium, where they may one day become part of new stars, new planets, and perhaps even new life. Neutron stars, then, are not just relics of the past. They are active participants in the cosmic cycle of matter and energy. They spin, they pulse, they collide, and in doing so, they shape the universe around them. Their existence is a reminder that even in death, stars continue to give, their remnants becoming the building blocks of future worlds. As we prepare to delve even deeper into the science of these incredible objects, let the image of two neutron stars orbiting one another lull you into a state of calm. Their dance is slow, measured, a ballet that has been unfolding for eons and will continue for eons more. And though their final embrace is violent, it is also creative, a moment of destruction that gives rise to new possibilities. We will now explore the limits of neutron stars, how massive they can become before collapsing into black holes, and what happens when they push the boundaries of physics itself. But for now, Let the steady pulse of a distant neutron star carry you into a deeper relaxation. A reminder that even in the vast and sometimes chaotic universe, there is order, there is rhythm, and there is beauty in the dance of the cosmos. Contemplate the boundaries of existence itself, where neutron stars dance along the razor's edge between being and nothingness. There comes a point when even these incredibly dense objects can no longer withstand the relentless pull of gravity, when the inward crush becomes too great and the star crosses the threshold into becoming something else entirely. This is the story of neutron stars at their limits, where physics bends, where matter transforms, and where the universe reveals one of its most profound secrets. Every neutron star exists in a delicate balance between two titanic forces. On one side, gravity, the relentless crush of the star's own mass, pulling inward with unimaginable strength. On the other, quantum mechanical forces, the Pauli exclusion principle that prevents neutrons from occupying the same quantum state, creating an outward pressure that resists collapse. This balance is so precise that even a small change in mass can tip the scales. For most neutron stars, this equilibrium holds for millions, even billions of years. But there exists a critical point, a maximum mass beyond which no neutron star can remain stable. Physicists call this the Tolman-Oppenheimer-Volkoff limit, named after the scientists who first calculated it. While its exact value remains uncertain, current estimates place it somewhere between 2 and 3 solar masses. Crossing that threshold means the neutron star can no longer support itself. The quantum pressure that once held gravity at bay becomes insufficient, and in a fraction of a second, the star collapses further, vanishing behind the event horizon of a black hole. It is a silent transition, observable only through the sudden absence of the star's telltale pulsations, or the burst of gravitational waves that might accompany its final moments. But right up to that threshold, neutron stars flirt with extremes that challenge our understanding of matter itself. As a neutron star approaches its maximum mass, its internal structure undergoes profound changes. The neutrons in its core are pressed so tightly together that they begin to overlap, their quantum wave functions merging until the entire core becomes a continuous medium rather than a collection of individual particles. At these densities, some theories suggest that quarks, normally forever confined within neutrons, might become deconfined, creating a quark gluon plasma similar to what existed in the first moments after the Big Bang. This hypothetical state, known as quark matter, could make the star even more compact, shrinking its radius while maintaining its mass. Some scientists speculate that there might exist quark stars, objects that have crossed the boundary from neutron matter to quark matter, but have not yet collapsed into black holes. These would be even stranger than neutron stars, their interiors a perfect fluid of free quarks flowing without resistance. While no definitive quark star has been identified, several candidate objects, like the enigmatic X-ray source, have sizes just slightly too small to be easily explained by standard neutron star models, leaving open the tantalizing possibility that they might be something even more exotic. Then there are the strange stars, a theoretical class of objects made not just of up and down quarks, but also containing strange quarks. These hypothetical stars would be even more stable than ordinary neutron stars, their strange quark matter acting as the true ground state of matter in the universe. According to some theories, a strange star could convert any normal matter it encounters into more strange matter, effectively growing over time. While no conclusive evidence for strange stars exists, their possible existence reminds us how much we still have to learn about matter under extreme conditions. The transition from neutron star to black hole is not always immediate or straightforward. Some models suggest there might be intermediate stages, exotic objects like electroweak stars, where the density becomes so great that the electromagnetic and weak nuclear forces unify, or preon stars, composed of hypothetical subquark particles. These ideas, while speculative, highlight how neutron stars push at the very frontiers of our physical theories, serving as cosmic laboratories for states of matter that cannot be recreated on Earth. Even the shape of a neutron star near its limits becomes distorted. As some neutron stars spin faster, particularly the millisecond pulsars that complete hundreds of rotations every second, they flatten at the poles and bulge at the equator, becoming oblate spheroids. The fastest known pulsar spins at 716 revolutions per second, its equator moving at about 24% the speed of light. At such extreme rotation rates, the star shape is significantly deformed, and if it were spinning just a little faster, centrifugal forces could theoretically overcome gravity, causing the star to fly apart. But perhaps the most dramatic way neutron stars approach their limits is through accretion, the gradual accumulation of matter from a companion star in a binary system. As gas spirals onto the neutron star's surface, it adds mass, pushing the star closer to its breaking point. This process often produces X-ray emissions, making these systems visible to telescopes as X-ray binaries. In some cases, the accumulated matter can trigger runaway thermonuclear reactions on the neutron star's surface, observed as X-ray bursts. Sudden flashes that can outshine the sun 100,000 times over in just a few seconds. Each of these phenomena, the maximum mass limit, the possible transition to quark matter, the distortions from rapid rotation, and the violence of accretion, paints a picture of neutron stars as objects constantly testing the boundaries of their own existence. They are cosmic tightrope walkers, balancing between known physics and uncharted territories, between stability and collapse, between visibility and the eternal darkness of a black hole. As we prepare to explore how these extreme properties manifest in observable phenomena, their emissions, their gravitational effects, and their role in the cosmic ecosystem, let the image of a neutron star at its limit linger in your mind. Picture it spinning furiously, its shape distorted, its interior a seething mass of exotic matter, hovering just on the edge of becoming something else entirely. It is a reminder that even in the cold vastness of space, there is constant change, constant tension, and a beauty that emerges from the struggle between opposing forces. As we float through the cosmic ocean, let us now turn our gaze to the light that neutron stars cast across the universe. Not just the literal radiation they emit, but the profound ways they illuminate our understanding of physics itself. These stellar remnants serve as nature's most precise laboratories, their extreme conditions revealing secrets about matter, gravity, and the very fabric of space-time that we could never discover on Earth. The light from a neutron star tells a story written in X-rays, gamma rays, and radio waves. Some pulse with such regularity that their timing can reveal the gravitational environment through which their signals travel. When a pulsar's game sweeps past Earth, the precise moment of its arrival carries subtle clues about the warped spacetime it has traversed. The Hulse-Taylor binary pulsar, discovered in 1974, provided the first indirect evidence for gravitational waves through its slowly decaying orbit, a discovery that would earn its finders the Nobel Prize and confirm a key prediction of Einstein's theory of general relativity. Consider the beautiful precision of a millisecond pulsar. Its spin so stable that the ticks of its rotation rival atomic clocks in their accuracy. These cosmic timekeepers allow astronomers to detect the most minuscule disturbances in their signals: the gravitational waves from distant supermassive black holes, the subtle tug of unseen planets, even the minute stretching and squeezing of space-time itself. Arrays of these pulsars form a galaxy-scale gravitational wave detector called a pulsar timing array, listening to the universe's background hum of colliding black holes and other cataclysmic events. The surface of a neutron star glows with thermal radiation, a cool blue-white compared to the fiery yellow of our sun. But this apparent coolness is deceptive. With surface temperatures around 1,000,000 degrees, a neutron star's thermal emission peaks in X-rays. The Chandra X-ray Observatory has captured stunning images of these stellar embers, their surfaces modeled with hotspots where the magnetic field channels plasma to the surface, creating regions that blaze with intense radiation. Some neutron stars, like the Magnificent Seven, a group of nearby thermally emitting neutron stars, glow primarily from this residual heat, their X-ray spectra serving as cosmic thermometers that measure their cooling curves over millennia. Then, there are the magnetostars, neutron stars with magnetic fields so intense that they can rip molecules apart from thousands of kilometers away. These cosmic powerhouses occasionally unleash starquakes that release as much energy in 1/10 of a second as our sun emits in 100,000 years. The December 27, 2004 event, for instance, briefly altered Earth's ionosphere from 50,000 light years away, a testament to the incredible energy these objects can unleash. Yet, even in their quiescent states, magnetostars emit a steady trickle of X-rays and gamma rays as their twisted magnetic fields gradually relax, like a cosmic spring unwinding over decades. Neutron stars also serve as natural particle accelerators. Their intense electromagnetic fields can accelerate charged particles to nearly the speed of light, creating beams of cosmic rays that streak across the galaxy. The Crab pulsar, the remnant of a supernova observed in 1054 AD, powers its surrounding nebula with a wind of relativistic particles that shines across the electromagnetic spectrum. This pulsar wind nebula acts as a giant fluorescent lamp, its glow powered by the spinning neutron star at its heart. Perhaps most remarkably, neutron stars have helped solve one of astronomy's longest-standing mysteries: the origin of heavy elements. For decades, scientists debated where in the universe could produce elements like gold, platinum, and uranium. The answer came in 2017 when the LIGO and Virgo gravitational wave detectors observed two neutron stars merging while telescopes across the world watched the resulting kilonova explosion. The spectra revealed telltale signatures of freshly synthesized heavy elements, confirming that neutron star collisions serve as cosmic forges for these precious materials. As we contemplate these luminous phenomena, let us reflect on how neutron stars illuminate not just the darkness of space, but the frontiers of human knowledge. They test our theories of dense matter, probe the limits of quantum mechanics and general relativity, and reveal the nuclear processes that create the elements of our everyday world. The gold in a wedding ring, the platinum in a catalytic converter, the uranium that powers nuclear reactors, all were likely forged in the violent mergers of these incredible objects. Time to explore the ultimate fate of neutron stars: how they cool over billions of years, how they sometimes find companions in the cosmic dark, and what happens when they finally meet their end. But for now, let the gentle pulse of a distant neutron star lull you towards sleep, its regular beat a reminder of the clockwork precision that underlies even the most extreme corners of our universe. The light from these stellar remnants has traveled across millennia to reach us, carrying with it stories of cosmic violence and rebirth, of matter pushed to its limits, and of the delicate balance that sustains our universe. As you drift toward sleep, imagine that light as a cosmic lullaby, whispering the secrets of neutron stars across the vast expanse of space and time. As we settle deeper into our cosmic contemplation, let us now follow the life cycle of neutron stars beyond their brilliant beginnings, into their long, slow fade across billions of years. Like embers cooling in the cosmic dark, these stellar remnants undergo an extraordinary transformation as they age, their furious births giving way to an eons-long journey toward ultimate stillness. In their youth, neutron stars blaze with the heat of their violent formation, temperatures exceeding 1,000,000 degrees at their surfaces and far hotter still in their cores. But unlike living stars, they have no nuclear fusion to sustain them. Instead, they cool gradually, their thermal energy radiating away into space, primarily through neutrino emissions from their superfluid cores and photon radiation from their surfaces. The first 1,000,000 years see the most dramatic cooling, as the star sheds the majority of its birth heat. During this time, its surface temperature plummets from over 1,000,000 degrees to about 100,000 degrees, still scorching by earthly standards, but a significant cooling nonetheless. The manner of this cooling tells a profound story about the star's interior. Initially, the dominant cooling mechanism is the emission of neutrinos, ghostly particles that stream effortlessly through the dense stellar material, carrying away energy at a tremendous rate. This neutrino flood originates deep in the core, where the extreme conditions allow for exotic processes like direct Urca reactions, where neutrons decay into protons and electrons, emitting neutrinos that escape into space. As the star cools further, photon radiation from the surface takes over as the primary cooling mechanism, and the neutron star's temperature decline slows to a more gradual pace. After about 10,000,000 years, most neutron stars become too cool to detect through their thermal emissions alone, their surfaces fading to temperatures below 100,000 degrees. Yet, they are far from dead. Many continue to reveal their presence through their non-thermal emissions, powered by their rapid rotation and intense magnetic fields. The oldest known pulsars, with ages exceeding 100,000,000 years, still pulse with remarkable regularity, their beams of radiation sweeping across the galaxy like the slow, steady ticks of a cosmic clock. Some neutron stars find companions in their old age. In binary systems where a neutron star orbits a normal star, the dense remnant can gradually accrete material from its companion, spinning up to incredible rotation rates in the process. These recycled pulsars, known as millisecond pulsars, achieve spin periods of just a few milliseconds, some completing over 700 rotations every second. The oldest of these objects may have been spinning steadily for billions of years, their precise rhythms undisturbed by the dramatic changes occurring in the universe around them. Isolated neutron stars face a quieter fate. As they cool, their magnetic fields gradually decay, weakening over hundreds of millions of years. Their rotation slows as they lose energy to electromagnetic radiation and particle winds. Eventually, after perhaps 1,000,000,000,000 years, even the most rapidly spinning neutron stars will have slowed to rotation periods of many seconds, their magnetic fields faded to a fraction of their original strength. At this point, they become nearly invisible, cold, dark spheres of ultra-dense matter adrift in an ever-expanding universe. Yet, even in this final state, neutron stars may retain some surprises. Theoretical studies suggest that the coldest neutron stars, those that have cooled below about 1,000 degrees, may develop exotic surface phenomena. Their crystalline crusts, under the influence of unimaginable gravity, could form perfect lattices with incredibly high thermal and electrical conductivity. Some models even predict that the surfaces of these ancient stars might superconduct at low temperatures, creating bizarre magnetic field configurations unlike anything seen in younger neutron stars. The ultimate fate of neutron stars remains an open question in astrophysics. According to some quantum theories, protons, though stable under normal conditions, might eventually decay over timescales exceeding 10 to the power 34 years. If this occurs, neutron stars would slowly evaporate over these unimaginable spans of time, their constituent particles gradually decaying into lighter particles and radiation. Other theories suggest that, given enough time, far beyond the current age of the universe, quantum tunneling effects might cause neutron stars to collapse into black holes, though this process would take exponentially longer than proton decay. As we contemplate these distant futures, let us return to the present, where neutron stars of all ages continue to teach us about the universe. The youngest, like the pulsar at the heart of the Crab Nebula, show us stellar death and rebirth in action. Middle-aged pulsars serve as precise cosmic clocks, probing the nature of gravity and interstellar space. The oldest, fated nearly to invisibility, may one day reveal the ultimate fate of matter under extreme conditions. Reflect on the broader significance of neutron stars, how they connect to the cosmic web of matter, how they've shaped our understanding of physics, and what they might still reveal about the universe's deepest mysteries. But for now, let the image of an ancient neutron star lull you toward sleep. A cold, dark sentinel orbiting silently through the galaxy, its incredible density a relic of a fiery past, its slow cooling a testament to the inexorable passage of cosmic time. Imagine it there, in the vast dark, a perfect sphere of ultra-dense matter, spinning perhaps once every few seconds, its surface temperature now just a few thousand degrees, its magnetic field still strong enough to deflect cosmic rays, but no longer powering brilliant beams of radiation. It is a reminder that even the most violent cosmic events eventually find peace, that even the densest objects must one day cool, and that across the unimaginable spans of cosmic time, all things change. As we drift deeper into the night, let us contemplate one of neutron stars' most profound gifts to the cosmos, their role as celestial alchemists, transforming simple matter into the heavy elements that make our existence possible. The gold in your jewelry, the platinum in medical devices, even the uranium that powers nuclear reactors, all were likely forged in the violent embrace of colliding neutron stars, scattered across the galaxy in brilliant kilonova explosions. The story begins with the Big Bang, which produced only the lightest elements, hydrogen, helium, and trace amounts of lithium. Stars later created heavier elements up to iron through nuclear fusion in their cores. But elements heavier than iron require a special kind of alchemy, one that doesn't release energy but consumes it. This is where neutron stars become nature's perfect crucibles. When two neutron stars spiral together in their final cosmic dance, their collision creates conditions unlike anywhere else in the universe. For a brief, glorious moment, temperatures exceed 1 trillion degrees, and neutron-rich matter is flung outward at nearly the speed of light. In this expanding cloud, atomic nuclei are bombarded by free neutrons in a rapid capture process called the R process. The R stands for rapid. Nuclei grow heavier by swallowing neutrons faster than they can decay, climbing up the periodic table to form gold, platinum, uranium, and other precious metals. The 2017 detection of gravitational waves from colliding neutron stars gave us a front-row seat to this cosmic alchemy. As telescopes around the world turned toward the source, they witnessed something extraordinary, a kilonova explosion glowing from the radioactive decay of freshly synthesized heavy elements. Spectroscopic analysis revealed telltale signatures of cesium, tellurium, gold, and platinum being created in real time. Calculations suggest the single event may have produced hundreds of Earth masses worth of gold alone. But neutron stars create heavy elements through more than just collisions. Their very surfaces serve as nucleosynthesis laboratories. The intense gravity of a neutron star can pull material from a companion star, creating an accretion disk where nuclear reactions occur. As this material builds up on the neutron star's surface, it occasionally undergoes runaway thermonuclear explosions called X-ray bursts, some of the most frequent thermonuclear explosions in the universe. These bursts create lighter heavy elements through the rapid proton capture process, contributing to the cosmic abundance of elements like strontium and yttrium. The material ejected by neutron stars doesn't simply vanish into the void. It becomes part of the interstellar medium, the cosmic reservoir of gas and dust from which new stars and planets form. Our solar system likely contains elements forged in multiple neutron star collisions that occurred before the sun's birth 4.6 billion years ago. In this very real sense, we are all made of star stuff, with a significant fraction coming from neutron star stuff. Some elements have particularly intimate connections to neutron stars. Iodine-129, a radioactive isotope essential for thyroid function in humans, has a half-life of just 15.7 million years, far too short to have survived from the Big Bang. Its presence on Earth means it must have been created relatively recently, in cosmic terms, before being incorporated into our solar system, likely in neutron star mergers. Similarly, the plutonium found in ocean crust points to relatively recent R-process events in our galactic neighborhood. As we prepare to explore neutron stars' final cosmic roles, let this thought carry you toward sleep. The calcium in your bones, the iron in your blood, and the precious metals we treasure all contain atoms that may have spent time in the unimaginable density of a neutron star. We are, in a very real sense, the universe becoming conscious of itself, and neutron stars played an essential role in making that possible. Neutron stars serve as cosmic laboratories, testing the laws of physics under conditions we could never recreate on Earth. But for now, let the knowledge that you carry pieces of these incredible stars within you lull you into peaceful rest. As we settle deeper into our cosmic reverie, let us now envision neutron stars as nature's most extreme physics laboratories, places where matter, energy, and the fundamental forces interact in ways that push the very boundaries of our understanding. These ultra-dense objects serve as testing grounds for theories that cannot be verified on Earth. Their extreme conditions probing the limits of quantum mechanics, general relativity, and nuclear physics. Within a neutron star's interior, densities reach such extremes that atomic nuclei lose their individual identities entirely. The star becomes one continuous quantum fluid where the distinction between one nucleus and another disappears, a state physicists call nuclear pasta. At different depths, this pasta takes on various forms. Near the surface, nuclei might resemble gnocchi, compact and round. Deeper down, they stretch into spaghetti-like tubes, and further still, they flatten into lasagna-like sheets. These bizarre configurations arise from the competition between the strong nuclear force and Coulomb repulsion, creating structures that cannot exist anywhere else in the universe. The core of a neutron star presents even more profound mysteries. Here, at densities exceeding those of atomic nuclei, neutrons themselves may break down into their constituent quarks. This quark matter, if it exists, would be a perfect fluid with near-zero viscosity, a state of matter that hasn't existed freely since the universe was microseconds old. Some theories suggest the quarks might form Cooper pairs, creating a color superconductor where color charge flows without resistance, analogous to how electrons flow without resistance in an electrical superconductor. Neutron stars also serve as natural laboratories for studying superfluidity. In their inner crusts, neutrons are thought to form a superfluid, a quantum state where particles move without friction. This neutron superfluid is likely responsible for the sudden speed-ups, called glitches, observed in some pulsars. When the crust's rotation slows due to electromagnetic braking, the superfluid core initially resists the slowdown. Eventually, the core and crust recouple through quantum vortices, transferring angular momentum in a sudden event we observe as a glitch. These phenomena provide unique insights into quantum behavior on macroscopic scales. The intense gravitational fields of neutron stars allow precise tests of Einstein's general theory of relativity. A neutron star's gravity bends light so strongly that we can sometimes see portions of its far side, an effect called gravitational lensing within the star's own atmosphere. The recent detection of a neutron star merger by gravitational wave observatories confirmed that these objects warp spacetime exactly as Einstein predicted, even during their violent collisions. Future observations may reveal even more subtle relativistic effects, potentially uncovering where general relativity breaks down and new physics must take over. Magnetars, neutron stars with ultra-strong magnetic fields, push our understanding of quantum electrodynamics to its limits. Their magnetic fields are so intense that they distort the quantum vacuum itself, affecting how light propagates through space near the star. In these environments, photons can spontaneously split or merge, and the vacuum becomes birefringent. Light's polarization changes simply by traveling through empty space. These effects, predicted by quantum field theory, but too weak to observe on Earth, become macroscopic phenomena near magnetars. Neutron stars may even help solve one of particle physics's greatest mysteries, the nature of dark matter. Some theories suggest that dark matter particles could accumulate in neutron stars over billions of years, eventually collapsing into a tiny black hole that would consume the star from within. The absence of such destruction in old neutron stars places important constraints on dark matter properties. Other theories propose that neutron stars could capture and concentrate certain types of dark matter, making them visible through unusual heating or energy emission patterns. As we contemplate these cosmic experiments, let us marvel at how neutron stars, products of stellar death, have become our guides to understanding the most fundamental aspects of reality. They test the laws of physics under conditions we could never recreate in terrestrial laboratories, probing questions about the nature of matter, the behavior of space-time, and the unification of fundamental forces. How do these neutron stars interact with their cosmic environment, the shaping nebulae, powering particle accelerators, and influencing star formation across the galaxy? But for now, let the image of these incredible natural laboratories lull you towards sleep. Ultra-dense spheres where the universe conducts its most extreme experiments, silently spinning as they probe the deepest mysteries of physical reality. As we drift through the cosmic ocean, let us now contemplate how these dense stellar remnants reach beyond their compact forms to influence the vast spaces around them. Like celestial sculptors, neutron stars shape their environments in profound and beautiful ways, energizing nebulae, accelerating particles to extreme velocities, and even triggering new star formation across galactic distances. Their influence belies their small size, proving that the universe often reserves its greatest impacts for its most compact objects. The most visible manifestation of a neutron star's environmental influence appears in pulsar wind nebulae, cosmic light shows powered by the star's relentless energy output. The Crab Nebule serves as the most magnificent example, its intricate filaments glowing across the electromagnetic spectrum, all energized by the young pulsar at its heart. This pulsar, spinning 30 times each second, generates a wind of relativistic particles that streams outward at nearly light speed. When these particles collide with slower-moving material ejected during the supernova, they create shock waves that produce the nebula's spectacular glow. The result is a constantly changing celestial artwork, with tendrils of gas and magnetic fields that shift perceptibly over human timescales. These pulsar winds represent some of the most efficient particle accelerators in nature. The rotating neutron star's intense magnetic field induces enormous electric potentials, capable of boosting electrons and protons to energies far beyond what human-made accelerators can achieve. Some of these particles eventually escape into interstellar space, becoming cosmic rays that travel vast distances across the galaxy. When particularly energetic cosmic rays strike Earth's atmosphere, they create air showers, cascades of secondary particles that scientists study to understand their extreme origins. About 10% of the cosmic rays reaching Earth likely come from neutron stars, their fingerprints revealed by specific energy signatures and composition ratios. Neutron stars also influence star formation on galactic scales, a surprising role for such compact objects. When a neutron star receives a natal kick from its supernova birth, it can plow through interstellar clouds like a cosmic cannonball. The resulting shock waves compress gas and dust, potentially triggering gravitational collapse in regions that might otherwise have remained quiescent. Some astronomers speculate that our own solar system's formation may have been initiated by such a shock wave from a nearby supernova, meaning a neutron star's distant ancestor could have played a role in creating the conditions for life on Earth. In binary systems, neutron stars dramatically alter their companion star's evolution. As the neutron star accretes material from its partner, it can heat the donor star's surface to extreme temperatures, creating unusual stellar types found nowhere else. Some of these systems evolve into ultra-compact binaries, where a neutron star orbits a white dwarf or even another neutron star in just minutes, so close that the entire system could fit within the volume of our sun. The gravitational wave signals from these tight orbits will be prime targets for future space-based detectors, offering new ways to study both neutron stars and gravity itself. The interstellar medium itself bears the chemical imprint of neutron stars' activity. The heavy elements created in neutron star mergers and surface explosions gradually mix with galactic gas clouds through turbulent processes and stellar winds. Over billions of years, this enriched material becomes incorporated into new generations of stars and planets. Spectroscopic studies of stars across our galaxy reveal patterns of elemental abundance that match predictions from neutron star nucleosynthesis models, tangible evidence of these dense objects' widespread influence. Perhaps most remarkably, some neutron stars may help regulate entire galaxies' evolution. When a neutron star forms near the center of a galaxy, its intense radiation and particle winds can contribute to feedback processes that limit star formation in the central regions. This mechanism, more commonly associated with supermassive black holes, may also operate on smaller scales through neutron stars, helping shape the population and distribution of stars in galactic cores. As we prepare to explore neutron stars' more speculative and exotic possibilities in our final messages, let this vision of cosmic influence lull you towards sleep. Imagine these dense stellar remnants as quiet architects of the galaxy, their subtle but persistent effects weaving through interstellar space over millions of years. Though small in stature, they shape their environments as profoundly as any giant star or black hole. A reminder that in the cosmos, size does not always determine significance. The realm of theoretical possibilities is vast, exploring hypothetical neutron star phenomena that push the boundaries of known physics. But for now, let the image of a pulsar's wind nebula comfort you. Glowing filaments expanding slowly through space, their gentle illumination a testament to the enduring influence of these remarkable objects. As we near the end of our cosmic journey together, let us venture beyond established knowledge into the realm of theoretical possibilities, where neutron stars may harbor phenomena so strange they challenge the very foundations of our understanding. In these final contemplations, we explore ideas that currently exist only in equations and simulations, yet could one day revolutionize how we perceive these ultra-dense objects. Some theorists propose that under certain conditions, neutron stars might contain cores of strange matter, a hypothetical state where up, down, and strange quarks coexist in perfect equilibrium. This strange matter, if stable, could represent the true ground state of matter in the universe. A neutron star with such a core would be fundamentally different from ordinary neutron stars, potentially more compact, with a sharp boundary between the quark matter interior and the neutron-rich exterior. These strange stars might even have surfaces of bare quark matter, lacking the conventional crust of atomic nuclei found on normal neutron stars. The concept of strange stars leads to an even more dramatic possibility, the strangelet hypothesis. If a strange star's surface is indeed bare quark matter, any normal matter contacting it could be converted into more strange matter through a cascading process. In theory, this could transform an entire neutron star into a strange star over time. Some have speculated, with much debate, that certain unusual stellar explosions could represent such conversion events, though no definitive evidence exists. Another frontier involves quantum phenomena on cosmic scales. The immense gravitational fields of neutron stars might amplify normally negligible quantum effects to observable levels. Some models suggest that neutron star cores could exhibit macroscopic quantum entanglement, where large volumes of matter remain quantum mechanically connected across stellar distances. If detectable, this could provide the first evidence of quantum behavior on astronomical scales. Neutron stars may also serve as portals to studying extra dimensions. Certain string theory models predict that gravity could leak into higher dimensions at very small scales. The extreme densities near neutron star cores could magnify this effect, potentially producing observable deviations from general relativity's predictions. Precise measurements of neutron star sizes and masses might one day reveal these subtle signatures of higher dimensional physics. The interiors of neutron stars could host even more exotic possibilities. Some theories allow for the existence of cue balls, non-topological solitons composed of squarks that might have survived from the early universe. These massive, stable clumps of exotic matter could accumulate in neutron star cores over billions of years, gradually altering the star's properties. Other speculative ideas include the existence of preon stars, objects even denser than neutron stars, composed of hypothetical sub-quark particles. Magnetitars push the boundaries of known physics in their own spectacular ways. Their magnetic fields may be strong enough to distort the quantum vacuum itself, producing measurable changes in light propagation near the star. Some models suggest that under such extreme conditions, virtual particles from the quantum vacuum might become real, leading to spontaneous particle production, a phenomenon normally associated with black hole horizons. As we contemplate these speculative frontiers, let us remember that today's theoretical possibilities often become tomorrow's observational certainties. The study of neutron stars has repeatedly shown us that the universe is stranger than we can imagine, and that the most outlandish sounding ideas sometimes turn out to be true. They are celestial storytellers, whispering secrets about our own cosmic ancestry. These ultra-dense remnants connect us to the grand narrative of the universe in ways that transcend mere scientific curiosity, touching on the very origins of our material existence and the extraordinary chain of events that made life possible. Consider the iron coursing through your bloodstream at this very moment. Each hemoglobin molecule contains 4 iron atoms. And, statistically speaking, many of those atoms were likely forged in the last frantic moments of a massive star's life before it collapsed into a neutron star. The gold or platinum in any jewelry you might wear probably originated in the violent collision of 2 neutron stars that occurred billions of years before our solar system formed. These personal connections transform neutron stars from distant curiosities into intimate relatives in our cosmic family tree. Violent ancestors whose explosive deaths made our biological existence possible. The timescales neutron stars reveal are equally humbling. The oldest known pulsars have been spinning with metronomic regularity since the Jurassic period, when dinosaurs still roamed Earth. They will continue their steady rotations for billions of years after our sun has faded, outlasting not just human civilization, but potentially all stars currently shining in our galaxy. Contemplating such longevity puts our fleeting human concerns into perspective while simultaneously highlighting the incredible fortune of our temporal placement, alive during the cosmic sweet spot when we can both observe neutron stars and understand their significance. Neutron stars also exemplify humanity's most noble intellectual pursuit, the desire to understand our universe simply for the joy of knowing. The story of their discovery reads like an epic poem of human curiosity, from Jocelyn Bell Burnell's initial detection of puzzling radio pulses to the gradual realization that these signals came from city-sized stellar remnants, to the recent triumphant detection of gravitational waves from merging neutron stars. Each breakthrough represents generations of scientists building on one another's work across cultures and continents, a testament to our collective genius when we focus our minds on comprehending rather than conquering. These stellar remnants also teach us profound lessons about balance and extremes. A neutron star exists in perfect tension between 2 fundamental forces: the inward crush of gravity and the outward push of quantum mechanical pressure. This delicate equilibrium mirrors the many fine-tuned parameters that make our universe habitable, from the precise strength of nuclear forces that allow stars to shine, to the exact balance of cosmological constants that permit galaxies to form. In studying neutron stars, we're really studying the boundary conditions that make complex life possible anywhere in the cosmos. Perhaps most importantly, neutron stars remind us that destruction and creation are intimately linked in the cosmic scheme. Every neutron star represents a stellar death, yet from these cataclysms come the elements essential for life and the energy that shapes galaxies. The same supernovae that obliterate stars also seed interstellar space with heavy elements. The same collisions that tear neutron stars apart produce the gold and platinum we treasure. This cosmic cycle of death and rebirth plays out on scales both vast and minute, from galaxy-spanning explosions to the radioactive decay of elements in our own bodies. As we prepare for our final reflections, let this understanding settle gently in your mind. When you feel the pulse at your wrist, remember it beats in rhythm with stellar pulsars far older than our species. When you breathe in the night air, know that your lungs contain atoms forged in stellar explosions that occurred before Earth formed. You are, in the most literal sense, stardust become conscious. And neutron stars played a crucial role in that alchemical transformation. As we continue our celestial contemplation, let us now expand our view to see neutron stars not as isolated curiosities, but as active participants in the grand story of cosmic evolution. These ultra-dense objects, despite their small size, exert influence across galactic scales and time spans, shaping the universe in ways we are only beginning to understand. Their role in the cosmic ecosystem reveals a universe far more dynamic and interconnected than we once imagined. The birth of neutron stars through supernova explosions represents one of the most significant energy release mechanisms in nature. A single such event can briefly outshine an entire galaxy, its shock waves propagating through interstellar space for thousands of light years. These expanding bubbles of hot gas create vast cavities in molecular clouds, simultaneously destroying existing star-forming regions while compressing adjacent gas to trigger new stellar bursts. Like cosmic gardeners, neutron stars and their progenitor supernovae prune and cultivate the galactic landscape, regulating the rhythm of star formation across the Milky Way. The heavy elements forged in neutron star mergers follow complex journeys through the interstellar medium. Recent simulations show these precious metals don't simply disperse uniformly, but instead flow along filaments of the cosmic web, concentrating in certain regions while leaving others relatively barren. This explains why some stars in our galaxy show higher concentrations of neutron star synthesized elements than others. They formed in neighborhoods particularly enriched by nearby mergers. Our solar system appears to have been fortunate enough to form in one such enriched region, benefiting from the cosmic gold rush of earlier neutron star collisions. Neutron stars also serve as crucial anchors in the invisible architecture of galaxies. Their precise positions and motions provide astronomers with reference points for mapping the Milky Way structure and gravitational field. The oldest neutron stars, those with ages approaching the lifetime of our galaxy, carry in their spatial distribution and velocities a fossil record of the Milky Way's formation and growth. By studying populations of these ancient stellar remnants, astronomers can reconstruct our galaxy's violent history of collisions with smaller satellite galaxies. Cosmic archaeology using neutron stars as artifacts. The energy output from neutron stars influence their local environments in surprising ways. Pulsar wind nebulae inject relativistic particles into surrounding gas clouds, affecting their chemistry and thermal balance. The intense radiation from magnetars can ionize interstellar gas over surprisingly large volumes, altering how that material responds to gravitational collapse. Even the cosmic rays accelerated by neutron star magnetospheres play a role in regulating star formation by heating molecular clouds and preventing premature gravitational collapse. Looking to the far future, neutron stars will be among the last sources of illumination in our evolving universe. As the cosmos expands and cools over trillions of years, after all stars have exhausted their nuclear fuel and faded to darkness, neutron stars will continue their slow cooling through thermal radiation and occasional accretion events. Their faint glow will provide the only visible light in an otherwise dark era, their steady rotation gradually slowing as they radiate away their angular momentum. Some may even survive into the hypothetical black hole era, when they'll finally succumb to quantum tunneling effects or proton decay, whichever comes first. In this penultimate contemplation, let us reflect on how neutron stars have shaped not just the physical universe, but the evolution of human thought and our understanding of cosmic reality. These extraordinary objects have served as both muse and teacher, pushing the boundaries of our knowledge while inspiring new ways of seeing our place in the grand scheme of existence. The discovery of neutron stars in the 1960s marked a pivotal moment in astrophysics, forcing scientists to confront the reality of matter compressed to nuclear densities. This revelation came at a time when quantum mechanics and general relativity were still relatively new frameworks, and neutron stars provided the perfect laboratory for testing their predictions under extreme conditions. The precise timing of pulsars confirmed Einstein's theory of general relativity with unprecedented accuracy, particularly in the famous Hulse-Taylor binary system, whose orbital decay matched Einstein's equations to within 0.2%. Neutron stars have also driven technological innovation. The need to study these faint, rapidly varying objects pushed the development of more sensitive radio telescopes, faster detectors, and better timing systems. Many of the digital signal processing techniques now ubiquitous in communications technology were first developed to extract weak pulsar signals from radio static. The global networks of telescopes used to study gravitational waves grew from earlier collaborations built to monitor neutron stars. Philosophically, neutron stars challenge our intuitions about matter and emptiness. A neutron star's incredible density means that if you could hold a teaspoon of its material, that tiny sample would contain about as much mass as all the buildings in New York City combined. Yet, despite this extreme concentration, neutron stars are mostly empty space at the quantum level, just like ordinary matter, only compressed to remove the vast distances between atomic nuclei. This paradox holds a profound lesson about the nature of reality. What we perceive as solidity is always, at fundamental levels, mostly void. The study of neutron stars has also given us new metaphors for understanding time and persistence. The oldest known pulsars have been spinning with near-perfect regularity for hundreds of millions of years, silent witnesses to most of Earth's complex history. Their longevity reminds us that while human civilizations rise and fall, while species evolve and go extinct, the cosmos continues its grand processes on timescales that humble our brief existence. Yet, simultaneously, the sudden glitches and star quakes that occasionally alter neutron star rotation remind us that even the most stable-seeming systems can experience abrupt transformations. As we prepare for our final reflection, let this dual awareness settle in your mind. Neutron stars embody both the incredible persistence of cosmic processes and their capacity for sudden change. They remind us that we inhabit a universe where stability and transformation coexist, where the same forces that create neutron stars also created the conditions for life, and where the most violent events often lead to the most beautiful consequences. As we reach the final moments of our year-long cosmic journey together, let us pause to fully appreciate how neutron stars have woven themselves into the grand tapestry of existence, connecting the quantum realm to galactic evolution, stellar death to biological life, and human curiosity to the fundamental workings of the universe. These extraordinary objects represent one of nature's most perfect syntheses of extremes, where the incomprehensibly small meets the astronomically large, where destruction and creation dance in perfect balance, and where the most violent cosmic events ultimately give rise to the conditions for life's delicate complexity. The story of neutron stars is ultimately a story about transformation, about how the universe recycles itself across vast scales of space and time. A single neutron star encapsulates this process perfectly. Born in the cataclysmic death of a massive star, its supernova explosion scatters newly forged elements across interstellar space, while leaving behind an ultra-dense remnant that will continue influencing its surroundings for billions of years. The iron in our blood, the calcium in our bones, and the precious metals we cherish all carry echoes of such stellar deaths, each neutron star collision contributing to the cosmic reservoir of elements that made planets and life possible. This grand recycling reveals a profound truth. We are not merely observers of the cosmos, but active participants in its ongoing chemical evolution. Our very bodies composed of atoms forged in these extreme environments. Neutron stars also embody the beautiful consistency of physical laws across scales and environments. The same quantum mechanical principles that govern electrons in atoms operate within neutron star interiors, albeit under conditions so extreme they produce entirely new states of matter. Einstein's equations of general relativity, tested daily in Earth's gentle gravity, predict with perfect accuracy how neutron stars warp space-time, even during their violent collisions. This universal applicability of physical law suggests an underlying unity to existence, a cosmic order that transcends location and scale, connecting the physics of our daily lives to the most exotic environments in the universe. Our exploration has revealed neutron stars as cosmic crossroads where multiple disciplines converge. Nuclear physicists study them to understand matter at extreme densities. Gravitational wave astronomers use them to test general relativity. Cosmologists track them to measure cosmic expansion. Chemists analyze their byproducts in meteorites and stellar spectra. Even philosophers ponder their implications for our understanding of time, matter, and the very nature of reality. This interdisciplinary richness makes neutron stars unique bridges between specialties, reminders that all branches of knowledge ultimately explore different facets of the same unified reality. The human story of neutron star discovery itself carries profound meaning. From the initial detection of pulsars, so regular they were briefly considered possible alien signals, to the recent triumph of multi-messenger astronomy, observing mergers through both light and gravitational waves. This scientific journey showcases humanity at its collaborative best. Generations of researchers across cultures building shared understanding through curiosity, creativity, and rigorous testing of ideas. The international networks of telescopes and detectors required to study neutron stars stand as monuments to what our species can achieve when we work together across borders in pursuit of fundamental knowledge. As we conclude, let us hold in mind the beautiful paradox neutron stars represent. Objects both incredibly dense and mostly empty space, both perfectly regular in their rotations and capable of sudden, unpredictable changes, both products of catastrophic violence and creators of life-enabling elements. They teach us that extremes often contain their opposites, that destruction and creation are inseparable partners in cosmic evolution, and that what appears as an ending is often a transformation into something new. May this cosmic perspective remain with you as a source of wonder and tranquility. When you look at the night sky, remember that invisible to your eyes, neutron stars pulse steadily in the darkness, some spinning hundreds of times each second, others completing just a few rotations every minute, all carrying forward the legacy of their stellar ancestors. Their faint signals travel across light years, whispering secrets about the fundamental nature of reality to anyone patient and curious enough to listen. And so we end where we began, with wonder. Wonder at these perfect cosmic laboratories, at the intricate chains of cause and effect that connect them to our existence, and at the human minds that have unraveled so many of their mysteries, while remaining humbly aware of how much remains to be discovered. May the quiet pulse of distant neutron stars accompany you into peaceful rest. Their steady rhythms a reminder of the beautiful order underlying our seemingly chaotic universe. Good night, and may your dreams be filled with visions of spinning stellar remnants, cosmic alchemy, and the profound interconnectedness of all things.